Noch eine halbe Drehung. Schnell.
Western Front, December 1944. Snow settles softly on the Ardennes forest, muffling sound and movement alike. Night presses in, heavy and unbroken, except for a low mechanical hum that refuses to fade. Along a narrow road, American tanks sit motionless in the dark, their engines still running. Exhaust drifts upward in pale clouds, briefly catching moonlight before dissolving into the cold air. Inside the steel hulls, crews remain awake, hands wrapped around metal mugs, boots resting against warm engine housings. The machines are not resting. They are waiting. Across the tree line, German tank crews observe through binoculars and rifle scopes. They expect silence. They expect cold engines, frozen fuel lines, and the ritual morning struggle to coax steel back to life. Instead, the Americans idle through the night. Hours pass. The engines do not falter. They do not choke. They simply continue. To the Germans, trained to shut down, conserve, and maintain with precision, the sight is unsettling. Engines were not meant to run endlessly in winter, not without consequence. And yet these do. What they are witnessing is not recklessness. It is a different philosophy of war, one built not on perfection, but on endurance. And to understand why these engines keep running, the story must begin years earlier, before the snow, before the forests, before the first American tank ever crossed into Europe. The assumptions of German armored power. In the early years of the war, German armor doctrine was built on a belief that bordered on certainty. Tanks were not merely weapons. They were instruments of precision, designed, engineered, and maintained to exacting standards. They reflected a military culture that prized mechanical excellence and technical mastery. German crews were trained not just to fight their vehicles, but to care for them with near-industrial discipline. Engines were shut down whenever possible. Maintenance schedules were rigid. Every hour of operation was measured against wear, fatigue, and the expectation of future failure. This philosophy had roots long before 1939. Germany's automotive and engineering traditions emphasized efficiency, tight tolerances, and optimized performance. When war came, those values were carried directly into tank design. Early Panzer models, light, fast, and mechanically refined, performed exceptionally well in short, decisive campaigns. In Poland in 1939, then in France in 1940, German armor advanced rapidly, often covering distances that stunned their opponents. Breakdowns occurred, but the operational tempo was brief enough that maintenance units could recover and repair vehicles between advances. The Blitzkrieg campaigns reinforced dangerous assumptions. German planners believed wars would be fast. Engines would not need to run continuously for days. Supply lines would move forward in clean, controlled phases. The tank, in this vision, was a scalpel, not a hammer. It struck, paused, was serviced, and struck again. As the war expanded, tanks grew heavier and more complex. By 1943, vehicles like the Panther and Tiger embodied the pinnacle of German engineering ambition. Their Maybach engines produced impressive power, but they were designed with narrow tolerances and high-performance expectations. These engines demanded constant attention. Oil quality mattered. Fuel purity mattered. Cooling systems required careful monitoring. Crews were trained to listen for subtle changes in sound, to feel vibrations through the hull, to shut down at the first sign of stress. Under ideal conditions, the system worked. On testing grounds and short advances, German tanks were formidable, but the battlefield was rarely ideal. As distances increased on the Eastern Front and later in the West, operational reality began to strain theory. Long road marches, poor fuel, dust in summer, mud in autumn, and extreme cold in winter all attacked the heart of German armored strength, the engine. By 1942, reports from Russia were already warning of a silent enemy. Tanks lost not to enemy fire, but to mechanical failure. Engines overheated. Transmissions cracked. Fuel pumps failed. Crews were forced to abandon vehicles intact, destroying them only after they could no longer be moved. The assumption that precision could overcome endurance was beginning to fracture. Yet German doctrine did not fundamentally change. Maintenance remained sacred. Engines were still shut down whenever possible. The belief persisted that protecting the machine was the key to winning the war. It was a philosophy that had worked, until it met an opponent who viewed machines not as delicate instruments, but as expendable tools meant to keep moving, no matter the cost. And it was from that opposing philosophy that a very different kind of engine would soon enter the war. America's industrial philosophy and the engines that would not quit. Across the Atlantic, a different approach to armored warfare was taking shape. The United States entered the war later, but it brought something that Germany lacked, an industrial philosophy built on scale, standardization, and redundancy. Where German engineers obsessed over mechanical perfection in small batches, American designers embraced practicality. Tanks would not be flawless. They would not be delicate. They would be durable, maintainable, and above all, capable of running for long hours under conditions that would disable almost anything else. The M4 Sherman, the workhorse of the American armored forces, was a product of this mindset. Its design favored reliability over raw power and endurance over precision. Early models were equipped with the Continental R975 radial engine, an air-cooled gasoline engine derived from aviation designs. Unlike German Maybach engines, the R975 could tolerate fuel of varying quality, continue running despite dust, mud, or heat, and survive the occasional lapse in maintenance without catastrophic failure. Later models, like the M4A3, would feature the Ford JAV8, a water-cooled gasoline engine that combined more horsepower with the same philosophy of endurance. This was not accidental. American armored doctrine emphasized movement and the constant presence of mechanized units on the battlefield. Where German crews were taught to conserve, American crews were trained to press forward. Engineers, mechanics, and logisticians worked in parallel with combat units to ensure that fuel, spare parts, and trained personnel were always within reach. Maintenance was systematic but never halted operations. Tanks were expected to run for days, not hours. The operational rhythm favored continuity. The tank was a hammer, not a scalpel. North Africa became the proving ground. In 1942 and 1943, American armored units, many of them inexperienced, faced the mechanized forces of Germany and Italy. They discovered something remarkable. Even under extreme desert conditions, sand-filling engines, heat climbing over 50 degrees Celsius, and relentless operational demands, Sherman tanks kept moving. Breakdowns occurred, but they were fewer and less catastrophic than the Germans expected. Reports from captured German officers emphasized their surprise at this durability. In the harsh desert campaigns, a tank could run day after day, sometimes without a full shutdown, while German vehicles required constant care to remain operational. This endurance had a psychological effect as well. German tank crews, accustomed to managing every hour of engine life, observed their opponents seemingly immune to fatigue. American crews could advance after days of continuous operations, engines throbbing, tracks rolling over rubble and sand alike. The Germans had no equivalent doctrine. Their engines were prone to sudden failure if pushed beyond prescribed limits. Even the finest maintenance could not overcome the basic vulnerability of high-tolerance designs when tested against relentless motion. By the time the Allies landed in Sicily and later Normandy, this difference had become stark. American tanks, engines humming, fuel flowing, and spare parts readily available, could sustain tempo in ways the Germans could not match. Each engine running continuously was more than a mechanical triumph. It was a strategic lever. Battles were increasingly decided not by gun caliber or armor thickness, but by which side could keep its vehicles moving while the other faltered. The stage was set. German crews would soon confront these engines firsthand, in forests, fields, and cities, and witness the practical philosophy of American war-making collide with their own ideals of mechanical perfection. The shock of seeing steel beasts continue day after day, unbroken and unyielding, would mark a turning point not just in the theater of war, but in the perception of what armored warfare could truly demand. Inside the M4 Sherman, a tank crew relied on more than training and discipline. They depended on the heartbeat of the machine beneath their feet. Engines were no longer abstract constructs of steel and pistons. They were living partners in the struggle. In cold mornings, when frost clung to the tracks and snow packed into the suspension, American crews climbed inside, lit the engines, and felt the hum ripple through the hull. Each vibration, each measured pulse of the radial or V8 reassured them. They could plan, maneuver, and fight without constant anxiety over a breakdown. Contrast this with German crews, whose lives were intertwined with the fragility of their tanks. Every hour of operation demanded vigilance. Crews were trained to listen for subtle metallic groans, to feel minute changes in the engine's rhythm, to anticipate failure before it struck. They lived in a state of constant tension, even during quiet hours, knowing that one missed maintenance task could immobilize their vehicle in the middle of combat. For Americans, the machine offered freedom. For Germans, it demanded submission. The human effect of this reliability cannot be overstated. Crews could operate longer, march further, and recover faster. Morale was bolstered by the certainty that their vehicle would not betray them, even after days of continuous use. Exhaustion still came, but it was psychological, not mechanical. In letters and diaries, American tankers frequently remarked on their faith in the Sherman, the strange comfort of engines that refused to fail. These engines became a silent ally, a reassuring presence that allowed men to endure the most brutal conditions of war. By the time German crews encountered them on European battlefields, from the hedgerows of Normandy to the snow-choked roads of the Ardennes, the human impact was undeniable. What the Germans could not understand was that trust in the machine was not naive optimism. It was engineered into every component, every design choice, every logistical calculation. At the heart of the Sherman's success was a philosophy that prioritized continuous operation over meticulous engineering perfection. The Continental R975 and later the Ford GAA engines were not designed to be the most efficient, quiet, or elegant. They were designed to survive. Air-cooled radials could tolerate sand, dust, and temperature extremes that would choke a Maybach engine. Oil consumption was higher, yes, but replaceable. Tolerances were deliberately looser, allowing the engine to continue running even when lubricants were thin or heat stressed the metal. These design choices reflected a broader American approach. Machines were tools, not works of art. Redundant systems, easy access to service points, and the ability to swap components in the field ensured that tanks could be repaired quickly without specialized facilities. American engineers understood that tanks were rarely stationary in war. Breakdowns were inevitable. But by accepting imperfection, they created vehicles that could be pushed to the limit repeatedly without catastrophic failure. German engineers, by contrast, aimed for technical elegance and power density. The Maybach HL230, for example, produced tremendous horsepower, but only under controlled conditions. Air temperature, fuel quality, and maintenance discipline all influence performance. Stray from the ideal, and catastrophic failures occurred. From this technological divergence came battlefield consequences. American engines kept running, sometimes for days, while German counterparts often stalled after hours of continuous operation. This difference transformed operational strategy. Reports from captured German officers and post-war memoirs frequently mention a single recurring theme: disbelief. German crews and commanders could not fathom how American tanks moved day after day without halting for repairs. They watched columns advance in rain, mud, and freezing temperatures, engines still warm and rolling, while their own vehicles broke down, sometimes within hours of deployment. Intelligence reports recorded astonishment at the mechanical endurance of U.S. forces. Officers wrote that the Americans seemed to operate on a different calculus of risk, ignoring fatigue in machines, accepting higher maintenance margins, and treating vehicles as expendable tools rather than sacred instruments. The psychological effect was profound. German crews became cautious, waiting for breakdowns that never came. They doubted their own doctrine. They recalculated tactics mid-campaign to account for tanks that did not stop, did not tire, and did not surrender the initiative. In short, American mechanical philosophy was an invisible weapon. It did not fire shells or pierce armor, but it created a persistent, relentless presence that German forces could neither ignore nor easily counter. Every mile of movement, every hour of continuous engine operation became a strategic advantage that gradually eroded German confidence and reshaped battlefield expectations. American tank endurance was not a miracle of metal alone. Behind every rolling Sherman lay a sprawling network of supply, repair, and support. Logistics were the invisible engine of American armored warfare. Fuel depots moved forward with astonishing speed. Recovery vehicles and field workshops accompanied every advancing column. Spare engines, transmissions, and tracks were staged at intervals calculated down to the mile. This system ensured that no tank remained idle for long, even if it did suffer mechanical trouble. In practice, this meant that Sherman crews could push their vehicles harder, confident that a backup was never far away. A tank running for days without stopping was not reckless. It was supported. Crews could operate continuously, relying on a combination of mechanical endurance and logistical foresight. German doctrine, by contrast, treated supply as an auxiliary concern. Their armies emphasized quality over quantity, precision over scale. When breakdowns occurred, replacement parts were not always available, and recovery was slow and dangerous. The contrast was stark. American tanks moved with momentum. German tanks often lagged, immobilized by their own maintenance culture. This logistical advantage amplified the mechanical endurance of the Sherman. Engines could run longer, not only because they were reliable, but because the system surrounding them was designed for relentless operation. Fuel flowed, parts were ready, and trained personnel ensured continuity. Across North Africa, Sicily, Normandy, and the Ardennes, this invisible support network kept tanks alive, engines humming, and momentum unbroken. American commanders embraced movement as a principle of warfare. Unlike German doctrine, which emphasized deliberate, controlled advances, U.S. leadership recognized that operational tempo could itself be a weapon. Tanks were not only instruments of firepower, they were engines of initiative. Commanders encouraged crews to keep rolling, to exploit weak points, to maintain presence on the battlefield, and to trust their vehicles to endure what would normally be considered extreme conditions. This leadership philosophy required both faith in technology and a willingness to accept risk. Senior officers understood that machines would fail, but they also knew that constant motion imposed strategic pressure on the enemy. A column of Sherman tanks, engines running day and night, could force German commanders into reactive positions, stretching supply lines, exhausting crews, and revealing vulnerabilities. The human and mechanical endurance of the tank became inseparable from the strategic mindset guiding its deployment. Moreover, leadership extended into the daily management of crews. Officers trained their men to monitor engines, to anticipate minor issues, and to perform repairs quickly. The emphasis was not on perfection. It was on continuous operation, maintaining momentum, and using mechanical reliability as a tactical advantage. Every decision reinforced the underlying doctrine: keep moving or risk losing the initiative altogether. There is a subtle, often overlooked factor in the Sherman's advantage: morale. Reliability became a psychological weapon. For American crews, the hum of a functioning engine provided confidence and reassurance in a world defined by chaos. They could focus on the fight ahead rather than the fear of sudden immobilization. Fatigue existed, but it was manageable. Exhaustion did not compound with anxiety over breakdowns. For German crews, the experience was almost the opposite. Facing relentless columns of American armor that seemed impervious to time, terrain, and weather, German morale suffered. The knowledge that tanks could run for days, without stopping, without maintenance crises, eroded confidence in their own machines. Reports from Normandy and the Ardennes consistently mentioned German frustration at encountering vehicles that defied the rules of mechanical expectation. This wasn't simply admiration, it was psychological pressure. A tank that continues to move, undaunted by the battlefield, can sap the will of the enemy as effectively as any gun. By combining human trust, technological durability, leadership foresight, and logistical support, American forces created a layered advantage. The engines of the Sherman were not merely functional. They were instruments of endurance, tools that shaped strategy, morale, and battlefield outcomes. When German crews encountered these machines, the shock was profound. The difference in doctrine, design, and operational philosophy became immediately clear. Reliability itself could win battles. The Americans pressed forward, almost indifferent to terrain or weather, while German crews calculated every movement with trepidation. One notable engagement was the fight for St. Lo, a key objective in the American breakout. Sherman regiments advanced in coordinated columns along narrow country lanes. Their engines ran continuously, warming the hulls for crews and preventing the freezing of tracks and transmissions in early summer rains. German defenders attempted ambushes using concealed artillery, Panzerfausts, and anti-tank guns. Some tanks were hit, of course, but mechanical failures were exceedingly rare. A damaged engine could often be bypassed or repaired in the field with minimal downtime. For German observers, each Sherman that pressed forward, seemingly unaffected by the terrain and enemy fire, became a symbol of bewildering persistence. The tactical advantage this reliability conferred was immediate and measurable. German forces had designed their defensive positions expecting a rhythm. Tanks would advance, pause, resupply, and become vulnerable during maintenance cycles. They relied on this pause to launch counterattacks, coordinate artillery strikes, and exploit mechanical weakness. American doctrine ignored this rhythm entirely. Sherman columns ran continuously. Crews refueled and resupplied under fire, then moved on, engines humming, momentum unbroken. The Germans were forced to adapt on the fly. Every ambush that might have crippled a stalled tank became an encounter with a moving target. Vulnerable, yes, but never stationary long enough to exploit mechanical weakness. In many ways, Normandy became a laboratory for American armored philosophy. Logistics played a hidden but decisive role. Fuel trucks followed close behind tank columns, ensuring that engines could run without pause. Field mechanics moved in tandem with combat units, replacing tracks, repairing transmissions, and performing emergency fixes under shell fire. Every Sherman was not just a weapon. It was a node in a larger system designed to sustain motion. The Germans could destroy a tank, yes, but they could not stop the flow. American armored units moved like rivers through the bocage, relentless and adaptive, while German forces struggled to plug the gaps in their lines. Mechanically, the difference was stark. Panthers required careful attention to engine temperature. Overheat in the sun or mud in wet fields could disable them for hours. Tigers were vulnerable to cooling failures, fuel impurities, and even minor neglect. Shermans, by contrast, could run for days. The Continental Ardennes 975 radial could operate even under partial lubrication, tolerate fuel variations, and continue functioning despite mud and water ingress. The Ford GAA V8 further increased horsepower while maintaining reliability, allowing columns to traverse muddy lanes, ford shallow streams, and climb steep banks without interruption. German crews began noting in reports that a tank could operate far longer than anticipated, and that operational limits previously assumed in calculations were being consistently exceeded. Beyond machinery, the human element amplified this advantage. American crews learned to trust the machine fully, knowing that endurance was built into every component. Men could sleep in short bursts, eat in the hull, and still remain combat effective because the engine continued to do its part. German crews, meanwhile, were often forced into constant vigilance. Every hour of operation was measured against potential failure. In the same rainfall-slicked lanes, they would shut down engines to prevent overheating or oil starvation, losing precious initiative. They observed with growing frustration as American tanks, often older models or mechanically less sophisticated on paper, pressed on unceasingly. The Battle of Corentin exemplified this dynamic. Sherman regiments advanced for more than 48 continuous hours, alternating only briefly to refuel. Crews drove through flooded lanes and artillery-cratered roads, constantly moving against a German defense desperate to slow them. Panthers and Tigers attempted counterattacks, but found themselves isolated when engines overheated or transmissions failed. The American principle of relentless motion, not tactical brilliance alone, was decisive. Crews reported that the mechanical endurance of a Sherman allowed them to exploit gaps, flank positions, and sustain pressure that German units could not counter. Even the psychological effect on German officers became apparent in communications and post-action reports. Reconnaissance units observed American columns moving through mud, rain, and shell fire without pause, and infantry notes remarked on the impossibility of immobilizing these machines. When German forces finally destroyed a Sherman, it often was not because of mechanical failure, but because of concentrated firepower or sheer luck. German crews had expected the tanks to falter long before reaching the front. They did not. Each moving engine was a small but unyielding threat, wearing down defenses before guns could fire. By late July, the Normandy breakout had fully demonstrated the cumulative effect of endurance. American forces, using engines that refused to stop, pressed through hedgerow after hedgerow. German units could neither predict when a tank would fail nor halt its advance. The resulting dislocation in the German defensive rhythm accelerated the collapse of resistance. Commanders were forced to redeploy units constantly, patch lines that should have held, and adjust plans in response to the sheer persistence of armored motion. In operational terms, a Sherman that ran for days was more than a mechanical feat. It was a force multiplier, shaping the battlefield in ways that traditional calculations of armor and firepower could not anticipate. Amidst all this, crews on both sides understood the stakes intimately. American soldiers knew they were pressing advantages that no single weapon system could provide. Every mile moved without a breakdown translated into territorial gains, fewer casualties, and strategic leverage. German crews, conversely, began to internalize the limits of their doctrine. They could no longer rely solely on firepower or superior armor. Every stalled engine, every pause required by maintenance, became a vulnerability against a foe whose machines simply would not stop. By the time the Allies reached Avranches in early August 1944, the consequences of mechanical endurance were clear. Sherman columns had not only broken out of Normandy, they had reshaped the strategic map. German forces were retreating, not solely because of firepower, but because continuous movement had exhausted their capacity to respond. Logistics, leadership, and mechanical reliability converged in a single principle: motion as a weapon. In the fields and lanes of Normandy, it was evident that an engine that could run day after day was as decisive as any cannon. Normandy and the relentless advance of American armor. July 1944. The bocage of Normandy was a labyrinth of hedgerows, sunken lanes, and hidden German defenses. Rain had fallen for days, leaving fields turned to mud and narrow roads slick with clay. For both sides, the landscape was unforgiving. Tanks struggled to maneuver. Infantry slogged through waterlogged ditches, and artillery fire carved craters that could trap even the sturdiest vehicle. Yet in this chaos, American tanks moved with a relentless determination that surprised everyone who watched them, friend and foe alike. The breakout from the hedgerows had begun in earnest. Allied forces had endured weeks of grinding attrition, slowly pushing inland from the beaches of Utah and Omaha. Sherman tanks, the backbone of armored columns, were operating continuously, engines humming for hours on end. Crews were exhausted. Some had gone nearly 24 hours without proper rest, navigating enemy fire, treacherous mud, and shell-pocked terrain. Yet the tanks continued to roll. Their engines, air-cooled radials, and V8s refused to fail. The mechanical hum inside the hull became a heartbeat, steady and reassuring. German forces watched in disbelief. Veteran panzer crews, trained in the art of mechanical preservation, could not comprehend how these vehicles continued to move. The Panthers and Tigers were superior in armor and firepower, but their Maybach engines were temperamental. They required frequent shutdowns, careful monitoring of oil and coolant, and constant attention to avoid catastrophic breakdowns. In the past, these engines had been effective instruments of armored warfare, but here, in the muddied lanes of Normandy, they were liabilities. This relentless advance set the stage for the subsequent campaigns across France, toward the German border, and eventually into the winter of 1944. The Ardennes would test these principles under extreme conditions: cold, snow, and frozen fuel. But the lesson of Normandy had already been written. Mechanical endurance, sustained motion, and the integration of human trust with technological reliability had become a decisive factor in the outcome of armored warfare. What the Germans had assumed was superiority, engine power, precision, and technical mastery, was being challenged by a very different philosophy. Keep moving, and victory will follow. The engines of a Sherman had proven their worth. They had carried men and weapons, bridged distances that should have slowed armies, and forced the enemy into reaction rather than action. In Normandy, the turning point was not a single battle, nor a single heroic action. It was the accumulation of relentless motion, the persistent heartbeat of thousands of engines rolling forward day after day, refusing to rest even in mud, rain, or fire. The Germans would see this pattern again and again in the months to come, and each time, the result would be the same: disbelief, exhaustion, and eventual retreat. The Ardennes, winter 1944. Engines against the cold. December 16th, 1944. The Ardennes forest, cloaked in early winter fog, was silent in a way that felt unnatural. Snow had begun to accumulate, icing tree branches and coating narrow, winding roads with a slick layer of frost. German forces, under the command of Field Marshal von Rundstedt, launched their surprise offensive, the Battle of the Bulge. Panzer divisions moved swiftly at first, but the harsh reality of winter quickly challenged their famed engineering. Fuel thickened in tanks, oil became sluggish, and even the mightiest Maybach engines struggled in temperatures approaching -10 degrees Celsius. For the Americans, the scene was different. Sherman crews, long accustomed to endurance campaigns, faced the same cold, snow, and narrow lanes, yet their tanks, particularly the M4A3 equipped with 4 GAA V8S, continued to hum. Engines roared to life in sub-zero mornings, warmed the hull for the crew, and maintained mobility through snow-choked roads. Crews who had endured the hedgerows of Normandy now pushed through forests where even foot soldiers struggled to move. The engines did not complain. They did not falter. They simply ran. The psychological impact on German crews was immediate and profound. They watched from icy tree lines as American tanks advanced despite frost, sleet, and artillery fire. Tanks that should have stalled for hours on end kept moving. Each hum of a Sherman engine echoed against the cold forest canopy like a heartbeat of inevitability. German commanders, who had meticulously planned the offensive to exploit gaps in armor and to outmaneuver slow, maintenance-bound vehicles, found their assumptions shattered. Their tanks overheated, transmissions seized, and crews froze inside immobilized vehicles. The Ardennes became a stark demonstration of what relentless mechanical endurance could achieve. One iconic instance occurred near Bastogne. American units, often outnumbered and facing both snow and entrenched German positions, relied heavily on mobility to hold key crossroads. Shermans ran day and night, ferrying troops, supplies, and artillery, while continuously keeping German units off balance. The engines and the crew's trust in them were decisive. German attempts to encircle Bastogne were hampered not only by Allied resistance, but by their own mechanical limitations. Panthers and Tigers, formidable in power but delicate in endurance, could not sustain continuous advances through snow, mud, and frozen terrain. Sherman tanks moved where others stalled. Technologically, the differences were stark. Maybach engines and Panther tanks had been designed for performance, not endurance. Even minor lapses in maintenance could cause fuel pumps to seize or coolant to freeze. Hydraulic systems stiffened, electrical components failed, and mechanical breakdowns multiplied in cold weather. American engines, by contrast, were designed to tolerate imperfection. Air-cooled radials could survive a thin layer of ice. Water-cooled V8S were robust enough to operate in the harshest conditions without catastrophic failure. Crews could restart engines in the dead of night, move through forested roads, and continue combat operations without pause. The logistics that supported this movement were equally impressive. Supply lines, often precarious in winter, were reinforced by prepositioned fuel, mobile workshops, and recovery vehicles. Even when a Sherman did break down, it could be repaired or swapped in a matter of hours, rather than being abandoned. This allowed columns to maintain continuous motion. German forces, forced to pause frequently to maintain engines, lost initiative. Every stalled German tank was a delay. Every moving Sherman was a pressure point that could be exploited. The interplay between endurance and logistics became a defining factor in operational outcomes. Leadership amplified the effect. American commanders understood that mobility itself was a strategic weapon. Units were trained to exploit continuous motion, not just to fight static engagements. Tankers worked in shifts, crews rotated, and command structures prioritized keeping units moving even under extreme stress. The human and mechanical systems were integrated. Whereas German doctrine emphasized careful, measured advances, American officers embraced calculated risk, relying on machines that could sustain extended operations. Movement became momentum, and momentum became battlefield advantage. The moral and psychological dimensions cannot be overstated. German troops, Witnessing Americans maneuver through snow and ice for days without apparent fatigue experienced a subtle but decisive erosion of confidence. Each moving tank became a symbol of relentless pressure. Each engine that refused to die reminded them that even their finest tanks were vulnerable to disruption simply because they could not match this endurance. Reports from the period frequently mention the amazement and frustration of German crews. This wasn't bravado. It was a genuine recognition that American operational philosophy had introduced a form of warfare that relied as much on mechanical reliability as on firepower. Even when winter storms grounded infantry and immobilized vehicles elsewhere, American tanks continued to project force. Shermans ferried artillery pieces, transported reinforcements, and provided mobile support for infantry holding key positions in frozen villages. Engines running continuously became the backbone of tactical flexibility, allowing commanders to respond quickly to enemy attacks, exploit breakthroughs, and maintain defensive lines where stationary forces would have been overrun. German units could fight, but they could not move as freely. For every Panther that faltered or a Tiger that overheated, 2 Shermans continued onward, engines humming, advancing the front. The Ardennes offensive eventually stalled, but not because of direct combat superiority. German forces had underestimated the endurance of American tanks, both in terms of mechanical reliability and human coordination. The inability of panzer divisions to sustain movement through winter, combined with relentless pressure from Shermans that refused to stop, forced German commanders into reactive positions. The American advantage in mechanical endurance had transformed the battlefield. Momentum, maintained through continuous operation, dictated engagement, dictated strategy, and ultimately dictated the outcome. By the end of December, as snowdrifts rose along the roads of the Ardennes, a pattern had been established. The Germans had pushed hard, aiming to break through the American lines and seize Antwerp. But they were countered not only by superior numbers or firepower, but by machines that refused to yield to fatigue, terrain, or weather. American engines, built for endurance, backed by logistics, trusted by crews, had ensured that momentum could be sustained in conditions that would have immobilized any less reliable force. Every mile gained, every defensive position held, was a testament to a philosophy that placed motion above perfection, endurance above short-term superiority. The Ardennes would mark a turning point in the perception of armored warfare. German commanders and crews came to understand a hard truth. Endurance could rival armor thickness, reliability could equal firepower, and momentum could decide engagements before shells were even fired. For the Americans, the engines that ran continuously through mud, snow, and enemy fire were not just machines. They were instruments of strategy, pillars of doctrine, and symbols of an industrial philosophy that Germany had never truly confronted before. As the battle concluded and winter receded, the lessons of the Ardennes were clear. Sherman engines, radial and V8 alike, had proven that mechanical endurance could sustain operations in the most extreme conditions. The combination of design, logistics, leadership, and human trust had created a form of battlefield advantage that went beyond tanks themselves. It was a lesson German crews would carry through post-war reports and memoirs. In the conflict between motion and perfection, motion often prevailed. And with this, the stage was set for the war's final months in Europe. Advances into Germany, relentless pursuit across the Rhineland, and the ultimate collapse of German resistance, driven as much by machines that refused to stop as by the soldiers who rode them. As winter receded across the Ardennes in January 1945, the scale of what had transpired became clear to both sides. The American armored forces, whose engines had run through mud, snow, and endless hours of combat, had not only survived the German counteroffensive, they had imposed their operational rhythm across an entire theater of war. Sherman tanks, often derided in contemporary German assessments for their thinner armor or lighter guns, had proven their most decisive advantage lay not in firepower but in endurance. They had reshaped battlefields through motion, forcing German forces into reactive positions, exposing weaknesses in doctrine and highlighting limitations in machinery that had previously been invisible in short campaigns. Casualty and loss reports from both sides illustrate the impact. German armored units suffered disproportionately from mechanical failure in the Ardennes. Post-war analysis by the U.S. Army and captured German technical reports show that nearly 30 to 40% of Panzer and Tiger tank losses during the initial weeks were due not to enemy fire, but to immobilization caused by frozen fuel lines, overheated engines, and broken transmissions. Panthers, which under ideal conditions were formidable weapons, often failed to start after prolonged movement in cold weather. Tigers, heavily armored but mechanically fragile, required constant attention that the rapid pace of American advances did not allow. In contrast, American Shermans exhibited mechanical failure rates under 10%, even while operating continuously for days in sub-zero temperatures and across treacherous terrain. The numbers were stark. Reliability had become a decisive factor in operational success. Beyond raw statistics, the human cost underscores the significance of mechanical endurance. American crews were exhausted, but effective. Soldiers wrote in letters and diaries of nights spent sleeping briefly in hulls while engines purred, of maneuvering through enemy fire with a confidence born of faith in their machines. Morale, which is often intangible and difficult to measure, was amplified by this reliability. Crews knew that the Sherman would not fail them, even under conditions that had immobilized heavier, more perfect German tanks. German crews, by contrast, experienced repeated frustration and fatigue. Watching tanks fail mechanically, often after strenuous effort, eroded confidence and contributed to psychological attrition. Reports describe officers in panzer units acknowledging, almost reluctantly, that mechanical reliability was undermining the very foundation of German armor doctrine. Logistics, long the unsung hero of endurance warfare, played a decisive role in this outcome. American supply chains, meticulously coordinated, ensured that fuel, spare parts, and repair crews were always within reach. In Normandy, mechanics had been stationed along secondary roads to repair or replace engines, tracks, and transmissions without halting operations. In the Ardennes, mobile workshops and fuel convoys allowed Sherman columns to maintain momentum even in frozen forests and narrow, snow-choked lanes. German forces, whose doctrine emphasized maintenance but lacked the scale and redundancy of U.S. logistics, could not sustain comparable operations. A Panther that required a part could sit idle for hours, sometimes days, while a Sherman could often be repaired in under an hour and returned to service. These differences magnified the advantage of mechanical endurance far beyond individual battles. The psychological impact on commanders was equally profound. German officers, observing the relentless pace of American armored columns, began to reassess their expectations of armored warfare. Memoirs and post-war reports describe the disbelief that arose when Shermans continued to advance despite rain, mud, and artillery barges. Even when facing superior firepower, Shermans rarely halted long enough to become easy targets. German tactics, often predicated on anticipating mechanical failure or exploiting operational pauses, were rendered increasingly ineffective. The endurance of American tanks forced constant redeployment, fragmented command, and reactive decision-making. Operational initiative, once a hallmark of German armor doctrine, was ceded to machines whose engines refused to stop. On the Allied side, the strategic consequences were immediate. Continuous movement allowed American forces to press the advantage from Normandy through northern France, culminating in rapid advances across the Rhineland. The famous race to the Rhine was not merely a contest of speed or firepower. It was a demonstration of sustained operational capability, underwritten by engines designed to withstand extended use. Sherman units could exploit breakthroughs, ferry reinforcements, and maintain pressure on retreating German formations, ensuring that opportunities for counterattacks were minimized. Endurance became an invisible weapon, as critical to victory as artillery, infantry, or air support. The contrast between mechanical philosophies also shaped post-action assessments. German technical evaluations, captured and analyzed by the Allies, frequently singled out endurance as a decisive factor. Engineers lamented that their designs, while superior on paper, had been outmatched by vehicles built for continuous operation. The Maybach HL-230 engine and the Panther, capable of producing exceptional horsepower, had been rendered vulnerable by narrow tolerances and high maintenance demands. Tigers, designed as symbols of armored perfection, were equally fragile under continuous strain. Shermans, by contrast, were deliberately simple, robust, and forgiving. Their operational reliability allowed American forces to maintain combat effectiveness even when crews were fatigued, terrain was unforgiving, and weather was harsh. Numbers tell the story, but anecdotal accounts bring it to life. In the Ardennes, some Sherman regiments recorded 72-hour continuous operational periods, including movement, combat, and resupply, with engines operating nearly the entire time. Crews rotated only briefly, eating, resting, and performing minor repairs while the tanks continued to move. German officers, observing these columns, noted in interrogations that the persistence of the Sherman created a sense of inevitability. They could never predict when the American unit would pause, making defensive planning nearly impossible. Even heavy weather and artillery did not force the tanks to stop. The perception alone was demoralizing. The operational implications extended beyond individual engagements. Endurance allowed American armored units to exploit gaps in German defenses quickly, creating cascading effects across entire sectors. When one Sherman column advanced without interruption, it forced German reserves to react, often overextending lines or leaving other positions vulnerable. Continuous motion created tempo, an invisible but crushing pressure that dictated the pace of operations. German doctrine, focused on preservation and precise maintenance cycles, could not counteract this principle. Where German forces had once relied on periods of rest and recalibration, they now faced opponents who did not pause. The battlefield had changed, not merely by tactics, but by philosophy. This was particularly evident in urban engagements. Towns like Bastogne, Saint-Vith, and later Cologne were fought not solely with firepower, but with the capacity to maintain operational momentum. Sherman's engines humming through the night could deliver reinforcements, evacuate wounded, and rotate artillery with unmatched efficiency. Even when immobilized temporarily by enemy fire, repair crews restored mobility rapidly. German counterparts, unable to maintain such tempo, faced a relentless advance that eroded defensive cohesion and morale. What seemed on paper to be minor differences in engine design or doctrine had translated into profound operational outcomes. By mid-January 1945, it was evident that mechanical endurance had not only shaped the outcome of individual engagements, but had influenced the trajectory of the European campaign. American forces were able to sustain continuous operations across hundreds of kilometers, from the Normandy beaches to the heart of Germany. German units, constrained by design, maintenance demands, and doctrine, were increasingly reactive. The war's momentum had shifted. Sherman engines, reliable under stress that would disable almost any German tank, had become an instrument of strategic advantage. The post-action analyses reinforced this conclusion. U.S. Army engineering reports highlighted that engine reliability and logistical support allowed operational tempos that would have been impossible with more delicate machines. Post-war German memoirs, from officers and engineers alike, frequently note a single, recurring theme. The Americans kept moving when German doctrine demanded pauses. The endurance of engines, the trust of crews, and the integrated logistics network combined to create a decisive advantage that went far beyond traditional metrics of armor thickness, gun caliber, or tactical ingenuity. In sum, the aftermath of the Ardennes and subsequent winter campaigns demonstrated that mechanical endurance could dictate the outcome of a theater of war. Shermans did not merely survive. They enabled mobility, sustained momentum, and preserved morale, all while forcing the enemy into reactive positions. By the time Allied forces crossed the Rhine, the lessons were clear. In modern mechanized warfare, machines that could endure, crews that trusted them, and logistics that reinforced them were as decisive as guns and artillery. As the final months of the European campaign unfolded in 1945, the full impact of mechanical endurance on the war became undeniable. American armored units, driven by engines that had run without pause for days and weeks, pressed relentlessly across Germany. Cities like Aachen, Cologne, and ultimately the Rhineland fell not only under superior numbers or artillery barges, but because mechanized units could sustain continuous operations that the German military could not counter. Tanks that had survived Normandy and the Ardennes carried the momentum forward, demonstrating that endurance in machines and crews could shape operational tempo, dictate strategic possibilities, and even influence psychological outcomes far beyond the immediate battlefield. The operational lessons for both sides were profound. German post-war analyses acknowledged the superiority of American logistical integration and mechanical philosophy. Engineers and officers noted that even Panther and Tiger units, superior in armor and firepower on paper, had been rendered vulnerable by operational limitations. Narrow tolerances, fuel sensitivity, and high maintenance demands had prevented sustained advances. In many cases, tanks had to be abandoned or destroyed, not due to combat, but because the operational framework could not sustain them. Reports from the Oberkommando to Heers, OKH, emphasized that mechanical failure rates had significantly reduced German initiative during critical campaigns, contributing directly to retreat and collapse. For American forces, the experience confirmed that operational doctrine had been correct. Machines were tools to be employed relentlessly. The Sherman had been deliberately designed for endurance, simplicity, and maintainability. Supply chains, field workshops, and recovery vehicles created a system in which engines could run almost continuously while crews remained effective. The success of this approach validated a philosophy that would influence post-war doctrine and tank design. Military theorists and engineers observed that the combination of mechanical reliability, integrated logistics, and crew trust created a multiplier effect, an operational advantage far beyond what armor or firepower alone could provide. The psychological effect extended to soldiers, officers, and commanders alike. American crews, accustomed to trusting their machines over long distances and continuous combat periods, gained confidence in both their equipment and themselves. This trust became a strategic asset, allowing commanders to exploit opportunities that would have been too risky in units with more fragile vehicles. German crews, conversely, faced the repeated frustration of immobilized tanks, stalled advances, and logistical bottlenecks. Each encounter with moving Sherman columns eroded confidence, slowed decision-making, and contributed to a growing sense of inevitability in the face of American operational momentum. These lessons were incorporated into doctrine almost immediately. Post-war American manuals emphasized endurance, maintainability, and the integration of logistics into operational planning. Tank design shifted to prioritize reliability over peak power alone, creating vehicles capable of sustained motion under combat conditions. Engineers studied failures in German designs and reinforced the principle that operational continuity could be as decisive as armor or firepower. Likewise, NATO forces during the early Cold War adopted similar philosophies, emphasizing robust engines, simplified maintenance procedures, and rapid logistical support, lessons drawn directly from the experiences of 1944 to 1945. On the German side, post-war assessments lamented the mismatch between doctrine and reality. While the design of the Panther and Tiger represented remarkable engineering achievements, their operational limitations had been exposed in combat conditions that favored sustained, relentless movement. Even the best crews could not overcome the vulnerability inherent in vehicles designed for short bursts of precision rather than continuous operation. Post-war memoirs frequently highlight the astonishment and frustration of German tankers, who observed American units advancing day after day while their own machines faltered under similar conditions. The lesson was clear. Engineering excellence alone cannot win wars if machines cannot endure the stresses of sustained combat. The broader strategic implications were equally significant. Endurance allowed American forces to dictate operational tempo, force German units into reactive positions, and maintain momentum across entire campaigns. This principle was evident not only in the Ardennes, but in the rapid advances through northern France, the Rhineland, and eventually into central Germany. Operations were no longer limited by the mechanical fragility of vehicles. Instead, planners could calculate strategy with confidence that armored units would remain operational under continuous stress. The cumulative effect of motion, reliability, and trust transformed the battlefield into a domain where endurance, not just firepower, dictated outcomes. Even in post-war military analysis, historians and engineers repeatedly cited the decisive role of mechanical reliability. Studies of armored campaigns in Europe highlighted that American tanks could sustain continuous operations for days under conditions that immobilized German vehicles. Comparisons of engine failure rates, maintenance demands, and operational availability revealed a pattern. Sherman tanks, despite being considered less powerful in terms of armor or armament, consistently outperformed German vehicles in sustained combat scenarios. These findings reinforced the principle that endurance could, and often did, outweigh raw specifications in determining operational success. The consequences extended to military culture as well. American soldiers developed a pragmatic relationship with their vehicles, emphasizing care without obsession, trust without complacency. Crews learned that a machine designed to endure could carry them farther, faster, and more effectively than a technically superior vehicle that required constant attention. German troops, in contrast, experienced repeated frustration, learning that the perfection of their machines was both an asset and a limitation, a lesson often recorded with grudging respect in post-war writings. Economically and industrially, the American approach also demonstrated its advantages. Standardization, mass production, and simplicity in design allowed replacement parts to be readily available, maintenance to be conducted in the field, and operational continuity to be sustained across thousands of vehicles. The Germans, producing fewer tanks with higher complexity, were unable to match this system in scale or speed. Even when individual vehicles were superior on paper, the lack of redundancy and the high sensitivity of engines to operational stress meant that American forces held the decisive advantage in both mobility and sustained combat potential. By the spring of 1945, as Allied forces crossed the Rhine and advanced into the heart of Germany, the practical lessons of mechanical endurance had been fully demonstrated. Tanks were no longer just instruments of firepower. They were embodiments of philosophy, doctrine, and industrial capacity. Sherman engines had kept running through mud, snow, and endless hours of combat, allowing operational tempos that German forces could not match. This endurance reshaped the course of campaigns, determined the outcome of battles, and in some cases decided the pace of the entire European war. The German recognition of this reality influenced post-war tank development, military strategy, and engineering philosophy across Europe. Engineers sought to design vehicles that could combine power with reliability, precision with endurance, and tactical superiority with operational continuity. Military planners recognized that the effectiveness of armored units was not measured solely by the thickness of armor or the caliber of guns, but by the capacity to move relentlessly, sustain pressure, and maintain initiative over extended periods. In the immediate aftermath, historians, engineers, and veterans alike would repeatedly return to the same lesson. The war in Europe, particularly in its final year, had been as much a contest of endurance as of firepower. Sherman engines that ran day after day, supported by robust logistics and trusted by crews, had created a force capable of dictating the tempo of operations and undermining even the most carefully engineered German defenses. In the calculus of modern mechanized warfare, reliability had emerged as a decisive factor, proving that motion, endurance, and operational consistency could rival, and sometimes surpass, traditional measures of combat superiority. Ultimately, the Ardennes and the push into Germany demonstrated that victory in mechanized warfare required more than firepower, courage, or technical perfection. It demanded systems that integrated human trust, engineering reliability, logistics, and doctrine into a single, cohesive operational capability. American forces achieved this through Sherman tanks whose engines refused to stop. The Germans, brilliant in engineering but constrained by doctrine and logistics, were forced to confront a principle they had not fully anticipated. Endurance, above all, could define the outcome of battle. The hum of a running engine can be as decisive as the roar of artillery. Across Europe, in mud-choked lanes, snow-laden forests, and rain-slicked fields, the unyielding motion of American tanks reshaped not only battles, but the way war was understood. Shermans, with engines designed to endure rather than impress, taught a lesson both simple and profound. Reliability could become a weapon. For the men inside, it was trust made tangible. Crews knew that the machine beneath them would carry them through fatigue, terrain, and fire. That trust allowed soldiers to fight harder, march further, and take risks their counterparts could not. For the enemy, it was disbelief turned into strategic disadvantage. German crews, trained in the art of preserving mechanical perfection, watched as their assumptions about armored warfare crumbled against the steady advance of engines that refused to fail. Mechanically, the lesson was equally clear. Engineering brilliance without endurance is fragile. The Panthers and Tigers, magnificent in design, could not withstand the relentless demands of continuous combat. Sherman's, simpler and less perfect, endured. Industrial philosophy, mass production, redundancy, field maintainability, proved as decisive as technical specifications. War in the modern era was a test of systems as much as of individual valor or firepower. The legacy extended beyond 1945. Post-war doctrine, tank design, and operational planning all absorbed this principle. Engineers would strive to balance power with reliability. Commanders would plan for continuous motion, and militaries worldwide would recognize that endurance shapes opportunity. The principle discovered in Normandy, proven in the Ardennes, and solidified across Germany became a foundation for mechanized warfare for generations. In the end, the story is not one of the largest gun or thickest armor. It is the story of engines that ran for days, of men who trusted them, and of battles shaped by unbroken motion. The war did not bend to perfection. It yielded to persistence. And through that persistence, the Sherman left its indelible mark on history, proving that in war, as in life, endurance often matters more than brilliance.